Hello, I'm Professor Pine. I'm going to show you that calculus is far easier than you might have thought. I'll tell you a little bit about my background. I'm a mechanical engineer who's worked in the aerospace industry much of the time. I'm a math teacher, and I have a tremendous interest in physics. And let's proceed right away with slope finding, because that is what calculus is at the start. So let's take a look at the definition of slope. Here is the line we are talking about, this line that's going up from left to right. All right, m is the letter that we use, and it is the length of the rise divided by the length of the run. That is how it's measured. M is the length of the rise divided by the length of the run for this line, and that's how slope is measured. Let's take a look at this example here now. Slope is measured with a reference of the Cartesian coordinates, the x and y axis. Let's take a look at this line first. It is parallel to the x-axis. It has a zero slope because it doesn't rise, nor does it fall, with reference to the x-axis. So if if it does not rise, then it's zero. Putting it into this equation here, the slope is zero. The rise is zero, the slope is zero. This, of course, applies to all lines parallel to the x-axis. Same thing, whether it's below or above, it has a zero slope. Now take a look at this portion here. You notice that the line rises from left to right. We call it positive. This applies to every angled line that rises from left to right. Could be from here this way or what have you. As long as it rises from left to right, it is positive. Now take a look at this portion here. Okay? And we look at this line here, which is parallel to the y-axis. That's not a slope, it's a wall, you might say. The run isn't there. It is zero. There's no run. So if you put in a zero where the run is in this equation here, you'll see that the slope is infinite. This applies to all lines parallel to the y-axis. And then the last case is this one here. Here, from left to right, the line is going downward, so it is a negative slope. All cases of lines fall between these cases here. Okay? Let's go on to the next. Let's see some of the uses of slope, and we'll take a look at this portion right here. Supposing you're earning $10 an hour, then your rate line is this one here in red. Notice that this line here goes from 20 to 50, and the difference between 20 and 50 is 30. That's the length. And this goes here between 2 and 5, this length here. So it's 3. So it's 30 divided by 3 is 10. Now, should you make this triangle here smaller or larger, the ratio is going to be the same. Your pay is not going to be any higher or lower. Now we'll go, supposing a person is making $20 an hour, so his line, his rate would be this line here. And this length here is between 60 and 100, so the length is 40. And between 3 and 5, there's 2. 40 divided by 2 is 20. It's $20 an hour. So that's the rate. So it's important how this line rises. what the angle of this line is very important. Now let's take a look at this portion here, another showing another thing about rate. Supposing you're traveling in a car at an average rate of 50 miles an hour. Well, this shows how many miles you will accomplish after this many hours. The first hour you will do 50 miles, the second hour 100 miles, and so forth. We're talking about the average in this case. So now this run is 2 between 4 and 6, and this rise is 100 between 200 and 300. So 100 over 2 is 50, right? Like this here. So you can also make a little formula here in your head that time is how many hours, 50 is the rate, and this is how many miles that you go. Every straight line has a simple formula, almost, well, just about like this, except these lines happen to go through the origin, 0, 0. Okay. Now, rates predict the future. They can predict the growth of a tree, the growth of a forest, or how fast a forest is being reduced, as the forests are being reduced now in countries like Brazil, unfortunately. And it can predict population growth, the death rate, the disease rate, the health rate, increase or decrease of a country's wealth, the absorption of oxygen by the ocean, the absorption of carbon dioxide by forests. These descriptions are unlimited, what they can describe. There could be the rate at which the ozone layer is disappearing, the heart rate of a person, and it could also illuminate the past. For example, we know of this so-called Iceman who fell in a crevice 3,000 years ago, or 4,000, whatever it is. He was found when a glacier melted on the border between Italy and Austria, and we can tell how long ago he died from carbon dating, which also could be illustrated the same way. So it could tell the past, the future, and so forth. Now, the thing is that most real-life situations are not straight lines. Let's take a look at this portion here. This might be the growth of a tree in years, and this is the height at which it's growing. The rate is definitely not constant. There's no straight line here. And the reasons why a tree would grow could be because it depends on the moisture that it's getting, whether it's competing with other trees for sunlight, and so on. And notice also that the height does level off at some time, and the tree will not grow any further, just like human beings and just like many living things. Now, take a look at this portion here where you have population rate, and you see this is not a straight line either. That is, of course, because people are giving birth, and each of which of those are giving birth to others, and so forth, and it's just climbing like this here, almost out of control in this world. And the death rate could be this way here because of advanced medical procedures and so forth, inoculations for children or what have you. These are not straight lines either. Then coming back to this situation here, the most pervasive thing in the universe, of course, is gravity. And this here will describe the distance that a body or an object falls some distance above the Earth. Here it is in time in seconds, and here is the falling distance. So in 1 second, it falls 16.1 feet, and so forth, and this is definitely not a straight line either. It goes according to this formula here, not counting air resistance. Okay? Now, in the engineering line, of course, I'm an engineer, and we'll take a look at this portion here. This here illustrates a beam that is encased in a wall. This is the wall, this is the beam here. It has a load on the end, marked by W. And it bends. The beam bends a certain amount. It is not visible to the naked eye, but it bends. We're talking about a structural member, not a piece of wood that bends, but a structural member. You can't see how much it bends, but it is bending. And according to the laws that are made in society for the structures, it can only bend so much, and more is not allowed, so therefore there are manuals that engineers have to go by in designing things. Now here is the length of the beam, and this is how much it deflects. Y is the amount it deflects in inches. W is the load on the end of the beam. L is the length of the beam. You notice that it's to the cube power. E is the modulus of elasticity. That is what the beam is made of. Is it steel? Is it aluminum? Is it wood? Is it what? This gives a description here. Then you have I, which is the cross-sectional properties of the beam, and that is the beam a rectangle, rectangularly shaped, or is it an I-beam or a T-beam or what have you? This is the description. This is not a straight line either, nor are most of the engineering formulas used for construction and for many other things. Hardly any of them are straight lines. So we are faced now with curves that we are going to look at. Now the simplest curve is this here one, y equal x squared. And let's look at it at this portion here. Okay? Here it's drawn up and it extends on upwards this way and this way, y equal x squared. For whatever value of x you have, you immediately know what y is, because here's the relationship is given right here. So for x is 1, y is 1, etc. 2, 4, and so forth. And it shows where the curve is and where the curve is not. Okay? Now let's examine a small portion of this curve right over here, and we'll illustrate it blown up over here so we could easily see it. Now we don't have to put this part in because we know what this will be as long as we know what x is. Now, take 2 points, one of them at x equal 1. Well, at x equal 1, y is 1. This is point 1 here. Now take another point at x equal 3. Now when x equal 3, y equal 9. We're going to measure an average slope between these 2 points. We can't do it along this curve here because we have to have a straight line in order to have the triangle. So we're going to use the formula where the rise is y2, that's this entire length here down to the x-axis, and y1 is this much. So this length is y2 minus y1, okay? And this length here is x2 from here to there minus x1 from here to here. That is that length. So the rise is this divided by that, okay? And we're doing it at the points x equal 1 and x equal 3. All right, here's the slope. The slope m is y2 minus y1, this line here, the length, and x2 minus x1, the length of this straight line here. 9 is from y2, minus 1, y1 here, and 3 minus 1 for x2 and x1. That gives this here, 3 minus 1. So you have 8 over 2, or 4. for the slope, the average slope between these 2 points. Okay? It's not an exact average really, but we'll call it an approximate average. Okay? Now here we go. Let's take a look at points between x equal 1 and x equal 2. We're going to find the average slope at these 2 points, x equal 1 and 2. I'm going to eliminate as much clutter as I can so you could get the point that I'm trying to make here. Now, point 2 is at x equal 2, so y is 4, because we're going according to this formula here all the time for these illustrations. Okay? Now the slope is y2 minus y1, 4 minus 1, and x2 minus x1, 2 minus 1. All right? So we have 3. The slope is 3 in a situation like this here, with x equal 1, x equal 2. Now let's take a look at this portion here. I'm going to leave out the straight line here. Now we're going to bring these 2 points much, much closer together, almost so that they're touching each other, very much closer together. And I blow this up so you can see it very clearly. All right? We're going to go now between the points x equal 1 and x equal 1 plus 1/10, 1.1. So 1.1, then y2, we immediately know is this squared, 1.21. Okay? So we're still using as an anchor this 0.1, which is x is 1, y is 1. We're still using this. Okay? Now we take the y2 and y1, put them in here, x2 minus x1, and notice here that we have a fraction in red over here. We have a fraction 1/10. In order to evaluate this here, we have to find the reciprocal of this, which is just merely 10. So now we have 10 times 0.21, it's 2.1. Okay? y2 was this here, 1.1, and now you have a slope of 2.1. Now the dots are very much closer together. Now, without the diagram, since they all look the same, we're going to bring those 2 points, that is, bring point 2 much closer together yet. Here, it's going to be at 1 plus 1/100th. x2 is going to be 1 plus 1/100th. Okay? Now, we know y2 is going to be this squared, and this is what it turns out to be. Okay? We put it into the formula again. And slope is equal to the same thing here. We're putting the same thing here, what the results are here. And notice that we now have 1/100th in the denominator. We have to use the reciprocal to evaluate it. So we have 2.01 now. x2 was 1.01. The slope is 2.01 on average of points that are very, very close together, only 1/100th apart. 1/100th of a unit apart. Now, find the slope now between points at x equal 1 and x equal 1 plus 1,000th. We're bringing the points even closer together. The formula is still the same. y2 is this squared, and we square it, we get this here. We put these all into the formula here, and we now have, to nobody's surprise, 1/1000th. We need the reciprocal of it. So here it is, and you have 2.001. From x equal 1.001, we have the slope of 2.001. Now the points are almost, well, you can't tell them apart. They're practically touching. And here we restate the same thing again. The number of zeros were the same. Yeah, here they are. Okay? Now, you might think that there's no point to this, but there is very definitely a point to this. Since each time I make the difference smaller, that means I'm bringing the 2 points closer. That means I'm adding more zeros in between, like 1.00000, etc., and a 1 at the end. The same number of zeros appear in the slope. We do this. Instead of the slope between points at x equal 1 and x equal 1 plus a million zeros in a 1, we say between x1 equal 1 and x2 equal 1 plus very tiny x. The very tiny x refers to the decimal point and a million zeros in a 1. Okay? 1 plus very tiny x. To find the slope, we have to find y2 as before. y2 is this squared, x2 squared. So we're going to square this here, even though there are words in here. We're going to square it. When we square this, this multiplied by itself is equal to this. 1 plus 2 very tiny x, you see, you square this by itself, you get that, plus very tiny x squared. Okay? Now we put it into the same formula. The slope is equal to such and such. We put it in here, and there's a minus 1 over here from x1, from y1 there, and x2 minus x1 here, and we get 2, and I'm going to abbreviate very tiny x because it's a lot to write down. Let's call it VTX. I'm going to abbreviate it. 2 very tiny x plus very tiny x squared over very tiny x. You see that this 1 is subtracted from this 1. This 1 is subtracted from this 1, and we have what's left here. So we're abbreviating very tiny x over here. Now I'm getting even tired of writing very tiny x, so let's now call it delta x. Okay? Delta x means very tiny x. It's not delta times x or x times delta. These two are together, like they're well, bonded together, and they only mean very tiny x. So we'll rewrite this here this way, okay? So slope is such and such here, just as it is here, and we have 2 plus very tiny x as the slope. Okay, now, supposing delta x, very tiny x, has a billion zeros in it with a 1 on the end. You know, a decimal point with a billion zeros and a 1. How does it compare to the 2? Well, it's virtually 0. We're going to do something that might be strange. We're going to cross it out. We're going to drop it, because compared to the 2, it's like nothing. And to make it even, those 2 points even closer together, they don't quite touch because you can't have, the 2 points can't touch, because if they do, then the distance between them is 0, and you're dividing by 0, which is not allowed. If you divide by 0 in math, you come up with crazy answers. But this is almost 0. Not quite 0, but almost 0. So, but we drop it anyway, and we are left with a slope of 2. That is the distance between 2 points so close together that an electron microscope can't see the distance between them. The only way you can see the distance between these 2 points is your imagination. So you might say, how could 2 points be 1 point or 1 point be 2 points? Well, that's the way God made it. And the same thing applies in physics. There's a certain particle, I understand, that is there at one place, but is not there, then it's at another place, or it's at 2 places at once. That's the way it was made. The usefulness of all of this here will become apparent very shortly. Now, let's try the same procedure, but this time the anchor point will be at x equal 2, and a tiny distance away, delta x, as before. 2 and a tiny distance away that you can only see in your mind. okay, for this very same formula here. And here is the illustration, okay. Here's the distance 2 to the curve. This is the curve we're talking about. And it is, we're getting, of course this is blown up to a huge amount, so you can see it, visualize it. And here's the tiny distance away for this dot here. This is blown up an enormous amount. If x is 2 plus delta x, this distance here, then y2 has to be that squared, because we're going according to this formula, right? Whatever x is, y is going to be that squared. So for this situation where x equal 2, we put it in this formula here as we had all the time, and we come up with this. And notice here, when we simplify it, that delta x comes out alone on the bottom all the time. And we also always end up with delta x alone in the denominator. Also, delta x is always added to find y2. That is to say, over here, this delta x is always added to whatever number we want to find y2, as in here. See, delta x is added to find y2, okay? Now, to evaluate this here, we come down to here. This is the same thing here. And we get 4 plus delta x. We drop this out as we did before. So m is equal to 4, the slope at x equal 2. Okay? We use the same procedure for the next anchor point for x equal 3 over here, and a small distance delta x away from it, as I explained before. So 3 plus delta x squared is y2, all right? And we fill in the numbers here. y2, of course, is 3 plus delta x squared, which is this. y1 is 9, and so forth here. We notice we have delta x alone again in the denominator, and we drop off the delta x here. We have a slope of 6 at the point x equals 3. Okay? We make a new request. What if we don't use a number like x equal 1 or 2 or 3 for an anchor point, but use any number, signify it by the letter, say, x? What would happen then? Okay? Let's give it a try and see what happens. So here, instead of the number that we're using before, 1, 2, or 3, we're going to use just x for any number. There it is here. And here is the function. And here's the delta x, which we always end up with. We multiply it through. Here's the original function plus delta x here. And here's the original function at the end. We multiply it through, and we are left with this part here, and we come out with 2x plus delta x. When we drop off the delta x as we had done, we find now that we have an x. We have a formula now. Slope is equal to 2x. And we also say, as delta x approaches 0, remember I said these 2 points are so close together that you can only separate them by thinking in your mind. That's how close they are together. They're almost 0, but not 0. Okay? And you might say, well, how can something be almost but not? How can 1 be 2? I have to leave that to philosophy, because nobody knows the answer to that. Now, isn't this m equal 2x a formula for the slope for all points on y equal x squared? Well, let's see if it is. Remember, at x equal 1, we found the slope was 2. At x equal 2, we found the slope was 4. At x equal 3, we found the slope was 6. You can see that each one of these are double what these are, just as this formula says. Whatever you put in here as the x value, that's what the slope is. So apparently this is the slope for all points. And if you try for any point along this curve y equal x squared, not just 1, 2, or 3, any point at all, x equal 16 or minus 10 or 0, you'll find that this formula here works perfectly. Now, is this result, this method, does this method work for only y equal x squared? Does this method work for other equations? Well, let's try this equation for example. I picked just any equation. We're going to use a shortcut here, and we're going to replace x by x plus delta x. You know what delta x means already, in the above equation to find y2. So x, wherever the x is here, we replace it by x plus delta x, as we had before. There it is here, where the x was, but the square, that's got to be here. It's got to stay here. The 3, that's here. And the x plus delta x replaces the x here. We multiply it out, we simplify it, we gather the terms, and here's what we get for y2. That's all this here. Here's the original equation over here. There's always got to be a minus sign there. Delta x is always in the denominator. We simplify it, and we come up with 2x minus 3 when we drop the delta x out. 2x minus 3. Now, since we use this process whereby we let delta x approach but not equal 0, and there is the need, we need it, we now call the slope dy over dx, okay, which means the ratio of a little distance in y divided by a little distance in x. In this last case, we now call it dy over dx equal 2x minus 3, as we had here, for this equation. For this equation. For the equation, for this equation here, which we just had, does this really tell us the slope at any point? And the point is the rate at an instant. Okay? So let's see. So I took this equation here and I drew it up here in this graph. Okay? And it extends upward this way. I also made a table here. For whatever x value, I evaluated what y is over here on minus 2, minus 1, etc., for various values of x. Okay? I also, over here, did this column for the slope, 2x minus 3, and I evaluated it right down here by whatever value of x is. I put it in here, and I got these values. Now, I compare these with this curve here to see if really the slopes at certain points are what this formula says it is. All right? The first point I looked at was x equal 3, and this is the point here. I drew a triangle up as accurately as I could and measured it as accurately as I could, and I found it to be, this triangle here is, of course, tangent to this line as best as my eye could do. And I find that it is 3 divided by 1, or 3. Okay? So the slope is 3 at x equal 3. Let's see if this is so. X is 3. The slope is indeed 3. Now, I took a look at a place where the bottom of this curve is, and the slope is 0 at a tangent at the very bottom here, and I found it to be at x equal 1.5. All right, let's see if this is true. When x is 1.5, the slope indeed was 0. Okay? So, you could check it in the formula here. If you have x 1.5, that's the same as 3/2. 2 times 3/2 is 3. 3 minus 3 is 0. Okay? Then I checked it at another point just to make sure, at x equals -1. X equal -1. I drew up a triangle as best as my eye could tell, and I came up with these values here. Notice the -3/4 because it's going in this direction here. Putting it in here, 3 3/4 is the same as 15/4, and -3/4 in the denominator, I come up with a slope of -5. And at point x is -1, the slope is -5, according to the formula. So anywheres that you care to measure along this curve, you'll find that this formula precisely tells what the slope is. Exact to any kind of exactitude that you are looking at. Okay, you can do this at home, a similar type of thing. Now, it's unwieldy, impractical to do this procedure for more complicated equations, especially since there is a shortcut. If you have an equation y equal x to the n where n is a number, then here's how you do it. You take the n and put it in front of the x as to multiply it, and take away 1 from the n over here, just as it is here. The derivative, and that's what it's called, the derivative, because it derives from this equation. The derivative is this here, n in front of the x, whatever the exponent is, and take away 1. So for a y equal x squared, the 2 goes in front of the x, take away 1, and you've got 2x to the 1, which is the same as 2x. So this is the derivative, the slope, at all points for this equation here, for y equal x squared. Now for this equation here, you do the same thing to each in its own turn. To each term, you do the same thing. 3 goes in front of here, take away 1, 3x squared, as it is here. Take this 2, put it in front. You must use whatever sign there is, leave it there. Take the 2 in front of the 3, and it's 2 times 3 is 6x to the 1, as here. Take the sign, whatever it is, put it there, and this is x to the 1 power. Take the 1, put it in front of here, it's 1 times x, but now the 1 minus 1 is x to the 0. Anything to the 0 power is 1, so there's a 1 here, over there. Now the derivative of a constant is always 0, so it doesn't apply here. This 1 comes from this x. Now the reason why the derivative of a constant is 0, that it drops out, is this. If you could imagine y equal 1, for instance, you'll know that it is a line parallel to the x-axis. If it's parallel to the x-axis, it has no slope. That's why it's 0, and that's why you drop this off. There's no magic involved. This is just merely a shortcut that must be used so one does not have to go through the delta x procedure. This is a shortcut. Constants alone drop out. Note that x is equal to x to the 1, and x to the 0 is the same as etc. here. As of now, what advantage is slope finding? Well, you don't have to measure on a curve, and measuring on a curve is much more difficult than it looks. You try measuring, putting a tangent line exactly on the point you're looking at and get the tangent line exactly at the correct angle. It's very difficult. You'll always make a mistake trying to do it that way. And you don't even have to graph the equation anymore, because you can just look at the equation and differentiate it. Now the slope is found quickly and easily and accurately by this method. It's found instantly. Now there's much greater advantages than I'm mentioning right now, or else we wouldn't be studying it. There's far greater advantages to doing this here. than are just listed here. But we have to go slowly to get up to speed. Now, differentiating, slope finding, or other form, that's the same as slope finding, differentiating, other forms of equations, we're going to look at that right now. Supposing you have a polynomial form, that is one term plus another term minus another term, and you could have 5 of these, and the signs don't have to be plus or minus, but this is just an illustration, a cookbook formula. The first term, you handle each term separately. First you do the first one, du dx here. Then you do the next one. Whatever the sign is, you put it in. Then you do whatever the sign is, put it there, and then you take the derivative of the next one. So the polynomial means there's many terms, and so you handle each term by itself. That's how that works. That's very easy. Now, here's the product form. And this is the formula for it, the cookbook formula for the product form, okay? I use this as an illustration here. This, of course, could be multiplied out, and you could use the polynomial form, but I'm using this simple one here as an example of how you use this formula here. You take the first term and put it there, as this cookbook formula says, you put it there. Then you take the derivative of the second term, and the derivative of this here, as we saw before, this is 1, the constant drops out, so there's a 1 there. Then there's a plus, you must use a plus, just as this formula says. You take the second term, v is the second term, that's what v stands for, and you put it in here, and you take the derivative of the first, and that's 2x, the constant drops out. So there it is if you have 2 of them. There is also a formula should you have 3 or more, but 2 is used 99% of the time anyway. So you multiply these out, gather the terms together, and you come up with this as the derivative of this equation here. And also notice that rarely does the derivative look or resemble the parent equation that it came from. Rarely does it resemble it. Now here's a quotient form. You have one thing divided by another, as in this illustration here. Okay? You have to use this cookbook formula here, where u is the numerator term and v is the denominator term. Whatever this formula is, you just follow it to get the derivative of the equation. So you take v, x plus 1, put it there, just as this says. You take the derivative of the numerator, which is 1, put it there. You must have this minus sign in. There it is. You take the u, the numerator, put it there, and the derivative of the denominator, which is 1, there. Then you square the denominator, as this says, right over there. Then you simplify, gather the terms together, etc., and you come up with this as an answer. This is the derivative of this. In this case, it looks a little bit like it also, but rarely does it look alike. Okay, so that's the quotient form. Now here's the power form. Should you have a term like this here, group of terms like this here, an equation like this, here's how you handle it. In this cookbook way, n is the exponent, which is 3/2. U is this entire term here, okay? So, nu to the n minus 1, etc. You take the 3/2, put it in front. There you did. You take the whole term, u is this whole term here, and put it in there, and you take away 1 from the 3/2. 3/2 minus 1 is 1/2. There it is there. And then you take the derivative of this entire formula here. This a is a constant. Letters other than x and y are usually constant. And this drops out, and you have minus 2/3 x to the minus 1/3, as it is here. You gather, simplify the terms, and you come up with this. This here is the derivative of this. Okay, again, it looks somewhat like this, but usually they don't. Now, here's another example here. Find the x value at slope equals to 2. Now we've done it, we've reversed the thing now for this equation here, okay, which we had done just before. This is the quotient form, which we found to be this. The derivative of this equation is this. And now we say the slope is 2. What's the x value? Well, this is the slope. So you replace this slope by 2, as we did here, and just solve for x. See, this is the slope. And we are told that the slope is 2. Now you solve for x, and we go along here. The 2 cancels this 2 here, or if you want to say, multiply both sides by a half, and they both, the 2's drop out, multiply it out, and you come up with x equals 0 and x is minus 2 for the slope is 2. This is what this says. Now I've drawn up this equation here, and it is this red line here going down to negative infinity, and this red line here going upward to plus infinity. Okay? As we can see, at minus 1, when x is minus 1, the denominator turns into 0, so the y is infinite. So this line goes straight all the way down, and this line goes all the way up. Now, I measured, I found here at x equals 0, here's x is 0, is right over here, and the slope indeed is 2 over here. And at x is minus 2, here's the slope finding thing, and it is 2 at these 2 points and nowhere else. So you could try it at home with any curves you want. You'll see that this is a precise way of getting the slope. Okay? This seems to be it for the first talk about it. I would like you to know that calculus is much easier than you think. Of course, there are very difficult problems in calculus, very difficult ones that nobody knows how to solve. But the understanding of calculus is not difficult at all. If you're faced with imagining can 2 points be 1 point or 1 point be 2, I mean, that's really the only difficult part, and you don't have to worry because nobody knows the answer to that anyway. And so I'll conclude by saying if you don't understand what I've explained here, just go over it again and again, and you'll have very little trouble understanding it. This is the one side of a coin in calculus. The other side will follow in a lecture following. Thank you very much, and do well.